Welcome to this explainer. Today, we're going to break down a really fascinating, highly theoretical paper that details the absolute boundaries of quantum hacking and encryption. You know, if you've been following the cryptography space at all lately, there's this underlying hope that quantum information is just going to swoop in and solve all of our classical security problems. But a groundbreaking new paper titled How Not to Build Quantum PKE in Minicrypt puts some hard mathematical brakes on that whole idea.
Okay, so let's dive right in and ask ourselves, is quantum mechanics really a magic wand that fixes all of our classical cryptographic limitations? I mean, for years we've heard that the incredibly strange properties of quantum physics, like the fact that it's literally impossible to perfectly clone a quantum state, offer this clear path to truly unbreakable security. But as we know, theory and reality are often two very different things, and this paper forces us to look at the rigid mathematical boundaries of what quantum encryption can actually pull off.
Section 1. The Quantum Cryptography Dream, Shattering Limits.
To really understand these boundaries, we first need to take a quick look back at the historical limits researchers have been trying to shatter. Tracing the evolution from 1989 to today, it's a pretty fascinating timeline. It all started back in 1989, when Impagliazzo and Rudich proved you actually cannot build classical public key encryption, or PKE, using just basic cryptographic building blocks. Then the 90s hit, and Shor's algorithm showed us that quantum computers could absolutely wreck our existing classical schemes. Naturally, this created a massive arms race to develop quantum PKE. Jump to 2022, and researchers proposed that creating certain quantum keys might be impossible, but their proofs relied on unproven conjectures. Now this new 2024 paper arrives, proving unconditional bounds on quantum PKE. So that initial dream that quantum information could effortlessly bypass classical limitations? Well, it's led us to a much deeper and far more complex understanding of our theoretical constraints.
Now, to grasp these constraints, we first need to define a concept known as minicrypt. Imagine minicrypt as this locked, completely barren cryptographic world containing nothing but the most basic tool imaginable: one-way functions. These are mathematical functions that are super easy to compute in one direction, but practically impossible to reverse. The holy grail for cryptographers has been trying to figure out if we can somehow build fully functioning quantum public key encryption while trapped inside this barren world of minicrypt.
Which brings us to Section 2, Stuck in Minicrypt, a structural catch.
So, while researchers recently showed it might actually be possible to build quantum public key encryption inside Minicrypt, it comes with a massive caveat. When we compare the two systems side by side, the catch becomes glaringly obvious. In classical PKE, which is the stuff securing the internet right now, public keys can be reused infinitely. You can publish a public key on your website, and millions of people can use it to send you secure messages. But these new quantum PKE proposals fundamentally rely on keys that are quantum states. And because of the no-cloning theorem in quantum mechanics, these quantum public keys are completely unclonable, meaning they lose their reusability entirely. Use it once, and it's essentially done. You just can't effortlessly authenticate and reuse them like classical keys.
All right, Section 3. Meet Quantum Eve, the ultimate hacker.
To demonstrate exactly why this reusability has to be sacrificed, the researchers engineered an unbelievable theoretical heist. Enter Quantum Eve. Her mission is basically the stuff of cryptographic nightmares. Her ultimate goal is to eavesdrop on a key exchange between two parties, let's just call them Alice and Bob, and completely break their quantum key agreement. The catch, she has to pull this off without Alice or Bob ever realizing their connection has been compromised. She literally has to leave absolutely zero quantum trace of her presence. To execute this heist, Eve relies on manipulating something called conditional mutual information, or CMI for short. You can think of CMI as the mathematical footprint of her eavesdropping. It is a precise measure of exactly how much Eve is learning about Alice and Bob's shared secrets. If the CMI gets too high, Alice and Bob's quantum states are altered, alarm bells go off, and Eve gets caught. So to succeed, Eve has to keep this mathematical footprint as close to zero as humanly or mathematically possible.
So how does she minimize that footprint? The researchers discovered she can use a brilliant framework to keep her conditional mutual information arbitrarily small. She does this by intelligently repeating her quantum queries and running multiple simulated copies of the receiver, Bob. By doing this, the CMI drops so incredibly low that her interference becomes mathematically undetectable. She remains completely hidden from Alice and Bob, acting essentially as a perfect ghost in the machine. Because Eve has kept her footprint so impossibly small, she unlocks a very powerful mathematical tool, an approximate quantum Markov chain. Think of it like a highly advanced predictive algorithm that perfectly anticipates the next link in a sequence. Utilizing this chain, Eve takes the intercepted data and successfully samples a fake Alice. She essentially creates a perfect mathematical forgery of Alice's viewpoint, and this allows her to perfectly fool Bob and extract their shared secret key. It's honestly mind-blowing.
Let's break down her exact heist framework, because it's a very specific three-step process. Step 1, she makes targeted quantum queries. Step 2, she leverages those exact queries to keep her conditional mutual information incredibly small. And step 3, she uses that low CMI to trigger a quantum Markov chain, successfully sampling a fake Alice to steal the key. This elegantly structured attack allows her to crack supposedly secure quantum encryption protocols that rely on nothing but basic one-way functions.
Which leads us to Section 4, Hard Quantum Limits, Busting the Myth.
By proving that Quantum Eve's attack actually works, the researchers left us with a series of hard impossibility theorems. First, they showed that a perfectly complete quantum public key encryption system using classical keys simply cannot exist purely from one-way functions, at least not without relying on some massive, unproven mathematical conjectures. Second, if you decide to use quantum public keys instead, they are fundamentally barred from being perfectly reusable. You are forced to sacrifice reusability if you want true security against Quantum Eve. And finally, if you try a hybrid approach, say classical keys but quantum ciphertext, it's utterly impossible to secure if the decryption process doesn't make active queries to an oracle.
Because of Quantum Eve's devastating attack framework, the paper leaves us with this really profound takeaway. A necessary condition for constructing such QPKE from one-way functions is to have the key generation classically unsimulatable. Putting that plain in English, the only way to build true, impenetrable quantum PKE in this barren world is to make sure the key generation process itself is so mind-bendingly complex that a classical computer couldn't even begin to simulate it.
This leaves us with an incredibly provocative final thought. We absolutely rely on the infinite reusability of public keys to make modern global communication scale. But if the ultimate quantum hacker proves that secure quantum public keys must inherently lose the reusability we take for granted every single day, how will we actually communicate securely in a post-quantum world? Are we going to have to redesign the entire architecture of digital trust completely from scratch? It's a massive puzzle, and for sure it's one the cryptography community is going to be trying to solve for years to come.